Okay, so good morning to everybody. First, thank you so much for the organizers to invite this talk to this very nice meeting. This is really a very nice opportunity to me and to ISA to engage with the microlensing community. As you know, our mission is not primarily designed for that. So in this talk, I will go through the current mission status and give some details about the Galactic Bulge survey requirements and the implementation layout. So these are just the credits to the Euclid consortium and to ISA. So if you click on these websites, actually you can get more details about the mission. So as you know very well, that Euclid is a dark energy mission. So it's basically testing the standard cosmological model. The big quest is to constrain the last 5 billion years when the accelerated expansion of the universe happens. So basically, gravity causes the structure to evolve over time, and you know that in the presence of dark energy, the structure evolution slows down. So there are two ways to measure that effect. One is through weak glancing, which is tracing the structure evolution of dark matter, and the other is galaxy clustering. Sorry, I'm just other way around. And so these are the two main cosmological probe the mission is made for. But there are also a lot of legacy science. I'm not going to go into details. So basically, Euclid is detecting for weak glancing 1 to 2 billion galaxies and about 20-25 billion for the redshift survey for galaxy clustering. It's a huge database which is basically multiplies by an order of magnitude comparing to earlier surveys for most of these topics listed here. I'm not going into the details of how the consortium is built up. This is the credit towards the consortium and to ISA. The Euclid spacecraft, it's a classical L2 spacecraft, so it has warm side and the cold side. It hosts a 1.2 meter Koch telescope, which is one of the best telescopes ever made in terms of stability. So it's very important that to measure shapes of the galaxy, it has to be not only diffraction limited, but also the variability of the spacecraft. So thermoelastic effect has to be very small and well characterized. So the main technology, enabling technologies, first of all, is the data link. So we have lots of pixels on board. So this is the 900 gigabit per day and the flight protocol to that. It's new technology. The image quality, as I mentioned, so the Koch telescope, the M2 mechanism, and the optics layout itself. And the third big technological investment is the AOCS itself to make the pointing jitter 25 meter second for a typical observation. So the science instruments, this and this, I'm just highlighting here the band passes. So this is the footprint of the Euclid Bliss imager, about half a square degree. You see, that's compared to the one footprint. This is the size of the moon on the plane, and this is some of the images from these observations. But this is a near-infrared instrumentation. It's for 3-band photometry as well as for sleeveless spectroscopy, which is shown on the right-hand side. And now just going quickly through that, we were very successful at the early mission phases. So the orbit injection was perfect using SpaceX Falcon 9 rocket, which was followed by 1 month of commissioning phase during the cruising from low Earth orbit to L2. And that was followed by performance verification, which ended on the 3rd of December 23. And then we had 72 days of so-called phase diversity calibration campaign, which I will, if I have time at the end, I will talk a little bit about. It's really essential for the PSF modeling. But during the commissioning phase, we had some anomalies, and I would like to talk about this a little bit because these anomalies have been mitigated, but to some extent they will stay with the mission. So the first one is some parasitic straylight were detected in the VIS instrument. And following investigation, it turns out that it's a reflection from one of the trusted bulbs on the left-hand side you see on the image. It reflects light to the backside of the sunshield, and from the sunshield into the inside of the cold compartment where the instruments are. It's an extremely low flux, 10 to the minus 9 watt per square meter information, but there's some small impurity, maybe a micrometeorite heat or just how the multi-layer protection was folded. Maybe there's some light paths which allows that. The mitigation is actually that we have to rotate the spacecraft a little bit more than it was originally intended, but we are still within the nominal angles. The other is that there is basically an X-ray of the spacecraft structure itself on the VIS detector. It's like a chest X-ray, especially when the solar X-ray activity is higher. And this happens because there are some lack of protection against X-rays in between solar cells. So there is nothing we can really do about that. But the good thing is that the solar activity, although we are close to a solar maximum, is still not that high, so we are not losing too much data. And if we lose data, then we can actually reobserve. And the third problem was that the guiding was not working perfectly because the fine guidance sensor was confusing basically guide stars with cosmic ray events, and a double imaging technique had to be to subtract images on board basically implemented, and we were really, glad to industry that it was a flexible way. They were flexible and they quite rapidly reacting to that, and finally we have a perfectly working FGS. And you see here the distribution of the pointing error, and we really better than the 75 millisecond 3 sigma requirement. So this is really a big achievement. In terms of key performances, and again, what really matters for the PSF, you see that it was yesterday or the day before yesterday, not yesterday, the 0.18 full bit half maximum, 0.80 millisecond full bit half maximum is measured after the telescope was put in focus. The relative photometric performance is better than the 1% required for the BIS channel. I'm not going to do much detail on that. And the same for the post-calibration error, relative photometric accuracy for this photometry. The spectroscopic performance is from the slitless spectroscopy shown here, but this is not really relevant to us, but all is compliant. What was a big challenge in 24 is that we noticed that the throughput of the telescope was going down in the visible channel in this, and you see that the variation was more than 10%. And then we implemented targeted decontamination, a heat up of 2 mirrors to get rid of the suspected eyes. And it was completely gone, but unfortunately it was coming back in a much faster way than before. And the reason of that is still not completely clear, but we had we had to implement again a decontamination campaign. Now with only forms 3, so only one optical element. And since in the last almost 8 months, we didn't have any problem in losing throughput. So the contamination management did work quite well. This is how the Euclid survey looks like. So it's a little bit under the required 14,000 square degree, because as I told you that because of the parasitic straylight program, we have to rotate the spacecraft and we cannot a little bit more. So the roll angle, it has to be between -3 and -8 degrees instead of between ±4. And the impact of that we are mapping, we lose a little bit of mapping efficiency with this. But the survey covers almost, well, we need an additional 4 months at the mission to get up to the 14,000 as required coverage. And this is what the survey status on the 10th of January. So these are the fields which have been observed already, and part of the data release one. So the highlights for 24 that Euclid moved finally into operations. The survey had to be highly optimized in order to mitigate the problem we had. The first data releases for the consortium and the community are planned. So the Q1 internal data release had to happen. And as I mentioned, the ice decontamination was successful. And the science highlights, so the early release observations has been released in the second batch with 10 scientific papers and 5 survey instrument reference papers you can access on the consortium and the ESA website. There is the Galaxy Zoom project. It's a community project to classify Euclid galaxies. The Cosmic Atlas of 280 gigapixel map have been released in October, and the Q1 internal release happened for 56 square degrees at November. This is only available to the consortium, but it will be available on the 19th of March to the general public, the Q1, which is more paths on the deep fields. And in October, we will have the internal data release one to the consortium members only. And in October 26, a year later, will be the first data release to the public. So what I would like to move now to the Galactic Bulge survey definition. Actually, there are time domain astronomy opportunities with Euclid. So every white field is actually observation with a cadence of about 600 seconds, and this is used by the solar system object pipeline to detect slow and faster moving asteroids. The Euclid deep fields are used for a number of science topics. We have also a medium deep field of about 70 square degrees, and an ecliptic, and the window to the ecliptic, which is probably the best ever data set to detect solar system object. This will be also released in data release one. And the external synergies with Rubin and of course the Roland. This is the context of the Galactic Bulge survey, which was actually discussed over the past decade, and but it accelerated the definition of the survey in 23 April. During the phase diagnostic calibration campaign, we had some slots for science and we wanted to include, but finally visibility was not in favor of us, so it did not happen. Then the Euclid science team adopted. Oops. Sorry, it's low battery. Okay, thank you. So then we defined the survey baseline starting from early 24. So there was a long technical evaluation and implementation design, and we got final approval by the Director of Science of ESA for the WIS only component. So the infrared data will not be observed. So this will be in disabled mode. And the implementation it happened in December and in the past weeks essentially. And now we have the date is the 23rd of March of the observations. So I would like to show the contributors who made basically the work that I'm going to present in the optimization on the program. And maybe there are many more from the Exoplanet Science Working Group, not listed here, but present here or contributed. So the motivation of having an early epoch with Euclid is that on the gain of a very small amount of observing time, which is actually something like 0.5% of the Roland program, if we would have done it September, then the constraints by measuring relative low-sense proper motions would be better, but still with the baseline that we are implementing it in March 25, the estimate is that the relative mass measurement precision is increasing by a factor of 2.8. So I think this is what was a really compelling motivation to do the Euclid survey. That the amount of time what we implement and actually the scientific gain for the community is really good. But there are some other science opportunities as well. Okay, the performance drivers. So first of all, that we only accepted requirements from microlensing when the survey was implemented. Basically, the survey location and the area coverage, it is following the Roman fields. In terms of reaching the required sensitivity in apparent motions, we need oversampling, and with 4 times repeating the standard reference observing sequence, it was concluded that that's sufficient, and the same setup is also sufficient to meet the photometric requirements. So this was basically the input we got from the exoplanet science working group. This shows a simulation that have the VIS image at this depth, and with the 16 details together after resampling would look like. The ESA and the consortium requirements were a much detailed list, and some of them I'm going to address now. So we may have to be sure. I mean, these initial requirements are still including that we have to include infrared data. Unfortunately, it did not happen at the end, but I will show you that we clarified and we cleared that the impact of persistence on the wide survey would have been acceptable level, but to programmatic reasons, essentially, that Euclid is not a survey. Euclid is a survey telescope. It has an observatory capability. The decision to deviate from the originally planned observing sequence, it has to be approved by the director of science, and this takes some time. So basically, this is a programmatic reason that at the very moment we don't have in the March implementation the infrared componenting. But we had to clarify that we can cope with guiding. So the fine guidance sensor can work in a very high stellar density of the Galactic Bulge region. We also had to clarify that the data rate what we are producing is still fine, and the compression time and the processing time by the computer of the VIS instrument can deal actually with the unusual content of the data, because it's a highly uncompressible data, so actually the data volume and the compression time is increasing. So in order to make we did tests of these aspects, and we're using the simple data model for dense and sparser fields in the Galactic Bulge. So all this work was coordinated by Emon and the exoplanet science working group. So these are the VIS simulations which were used for the compressibility test, and it turned out that if you do the standard 566-second observing time, then we cannot fit observations into the commanding scheme what we have. So we had to use the 400-second integration time, which is compatible with our commanding scheme. And just by changing a timeout command, we will not have any problem. The drawback, the advantage of having a little bit of shorter exposure time is that we have less impact from the cosmic rays, and we less impact from blooming effects. But we still do not have a large scale effect, the so-called illumination correction. So that calibration product has to be created, probably interconnected with, from two other exposure tanks for which we have calibration data. In order to ensure that we can actually downlink an increased volume of data, so we requested additional ground contact time after the observations. So instead of the 4 hours standard time, we have 5.5 hour antenna time, just to make sure that the data can be downlinked. The thermal impact, since we are observing only with this, there was a suspect that the internal heat load, if NISP is disabled, could be different from the nominal one, and that will slightly cool down the system and change the PSF into thermoelastic effect. But finally, we adjusted the cadence in a way that this will not happen. And also the external heat load modulation, which means that the sun direction is kept almost constant during the observations. So we are in a very stable condition. And also the solar aspect angle, it has been chosen at an angle where the stray light is really minimal. In terms of the guiding performance, so during the commissioning phase, we were close to the Galactic Bulge, and although not up to 8,000 or even 9,000 stars density, but 2,000 stars density were already observed. So we are sure that we can operate that one. And there is a little bit of risk still that something goes bad, but according to the FGS experts, the worsening failing guiding is not really what we expect. What could happen that from absolute tracking mode, we move to the so-called relative tracking mode, but from the quality of data, it's essential. There is no difference. The persistence impact analysis was done. So in order to ensure that what would have been the wait time if we implement the NISP component, there were two approaches. Is one to do simulations with the nominal persistence model, and the other is to derive the in-flight decay data from after observing a very bright object. So these are the simulations from a sparse and from a dense field of NISP. And it turned out that even waiting 2 days, basically with the standard model, we have far more pixels above the 2-electron persistence threshold that we cannot observe with NISP. But it was suspicious that this is actually overestimating persistence. And then the colleagues in the team made an analysis of observations of 59 images, which were obtained on a very bright 3.4 magnitude star. And the outcome of that, in the bottom, you see the counts minus the dark count subtracted. That is basically after half a day, it drops back to nominal 2-electron level, which is much quicker than the predicted persistence. And the reason of that is probably that the predicted persistence or the nominal persistence model is made of flat illumination, while we are using a point source for that. And this is actually very important for the NISP team to follow up later. Okay, and so this is the slot. So we had to ask the survey team to implement an empty slot of 1 to 2 days for the EGPS. So this is on the 23rd and 24th of March. And the footprint with the yellow and overlaid with the nominal case from the GBTDS from Roland is shown here. So we believe that since the Euclid footprint is bigger, it will be served an extra opportunity for Roland to actually fine-tune the location of the field. And this is how the orientation of the individual fields look like, overlaid with the Hipparcos positions. So we will measure 144 with exposures in total, with about 500 second cadence. So the exposure time is 400 seconds. And we have a little bit of overheads for slewing and for processing the data. But it's also very important that before and after we observe the PSF number 4 field exactly in the same setup. Not with 9 by 9, but just in one position with 16 liters. So that will be a thermally homolog position. So the spacecraft will be rotated around the sun vector only, so we don't change anything thermally. But that's a standard PSF field when the PSF retrieval could happen without the problem of confusion. The data processing plan is, first of all, we will produce the level 0 data, and we expect from the Exoplanet Science Working Group to do as quick as possible performance checks and to actually release a quality report and data validation products after 3 months. The SGS cannot touch the data until October, because there is no capacity for that. But after that, there is a coordinated effort between the working group and the SGS to produce standard products. And beyond October 25, we still don't have plans. About the communication, so there is no official announcement yet of the EGPS. It will be done when we can confirm that the data is actually fine. At least at the detail we can look at quickly. And this will probably happen shortly after 23rd of March. And coordination with NASA Roland, it will be started soon by the project scientists. The data release plan is that we want to make public the level 0 data. That's probably not within 1 year, but all this is really preliminary plans. So we start detailed planning once the data is actually available. And all I can say that the policy is to make it public within 1 year. Okay, and very quickly, I would like to talk about the point spread function modeling challenge for Euclid, because I think this is also applicable for you. You know that we have very stringent requirements in the knowledge error of the PSF. For ellipticity, this is 10 to the minus 4, so 1 part in 10,000. And there are 2 reasons that the PSF is varying. One is the chromatic variations, because it's a very broadband filter, and the other is the spatial temporal variation. So as the spacecraft is moving around, the sun direction is changing, very small. So actually, 1 nanometer optical path differences change the PSF at that way that the model has to follow that. The way it is actually done and implemented by the consortium is that there is a physically motivated model, which is shown on the right. So basically, that's a CAD model of the telescope. And since Euclid do not have a wavefront error sensing capability to follow up deviations from this fiducial model, there was this phase diversity calibration campaign at the beginning. So during 72 days, we measured wavefront errors in different attitudes of the survey, and these thermoelastic states are believed to be stable over the entire mission. And these wavefront errors, what we measured at the beginning, are applicable to the rest of the survey. At least this is what we hope for. And this basis set is used to actually to make a time-dependent, accurate model which is compliant with the weak lensing requirements. But at the end, it actually turned out that the spacecraft is not reacting very complicated to thermoelastic variations. It's mainly the focus terms, so lower the polynomials, technical polynomials can explain the thermoelastic variations. And this is just the last, just a highlight about the WIS PSF model. You see plus minus 8 RSEC log scale on the left and the zoom on the right. And you see the M2 spider diffraction spikes, but there's actually also very small surface errors from the M1 can be quite well modeled. So in terms of modeling choices, so you have from the EGBS data the PSF fields, which can be used for a data-driven approach to actually recover the PSF, or the consortium PSF model, can be used and actually tested on the PSF fields before and after the EGBMs. And I would like just to highlight that the SLAB symposium, if you are still interested in, you can register, will be just after the release of the Q1 public data in Holland. And yeah, thanks a lot.
Okay, I'm just going to check if we've got enough charge yet.
Right. Thanks very much, Roland. And time questions. I feel like I'm too close to it to ask the chair's question.
Well, so I suppose so. Just looking further ahead into the lifetime of Euclid, so you mentioned that there's going to need to be an extra 4 months of time for the main survey. Do we have a good idea how much lifetime may be in Euclid in principle?
Well, the main limitation is in terms of consumables. It's is the cold gas, which is used for the micropropulsion system to meet the 25 milliardsecond pointing requirement. But we can also operate only with reaction yields, then the degradation of the relative pointing error will happen. But for instance, in spectroscopy or in infrared observations, that could be still fine. Of course, also aging of the detector and maybe also aging of the optical system is an issue. Mission extension will be discussed 2 years before the end of nominal mission lifetime. So that will be more or less the time when also the community will be asked, and then about possibilities have to continue. But I also want to emphasize that actually, okay, the Euclid Galactic Bulge survey is a 1 day survey, a little bit more than 1 day, but we don't need extra. It doesn't mean that actually we even lose of that 1 day from the survey. Because the Galactic Bulge, it happens in a low stress area when we don't have a lot of fields to observe. So there is some unallocated time during nominal mission lifetime. And again, actually we are observing against this unallocated